What exactly is Retrieval-Augmented Generation, and why is every AI company suddenly talking about RAG? If LLMs like GPT, Claude, Gemini and Grok are already so powerful, then why do we still need another architecture on top of them? Today we are going to understand the complete architecture of RAG in the simplest possible way. And trust me, by end of this video, you will understand how modern AI assistants actually retrieve company knowledge, search documents semantically, and answers questions with real-time context. First, let's clear one important misconception. RAG is not a LLM, it's not a framework, and it's not a database either. RAG is simply an architecture or a technique that works together with LLMs. In simple terms, RAG improves the accuracy of LLM's response by retrieving prompt-related context from external data sources before generating the answer. That external data source is usually a vector database, and that database stores information in something called embeddings. Don't worry, if these words sound complicated right now, we'll understand everything step by step. Let's take a real-world example. Suppose we build a hospital chat assistant. Now the user asks, what are the ICU visiting hours? Here is what normally happens without RAG. The LLM may hallucinate. It may generate a confident but completely incorrect answer because the hospital's internal policy was never the part of model's training. So instead of depending only on the LLM memory, RAG retrieves the exact hospital policy first. Here is how. The user prompt first goes to an embedding model, like openai text embedding or Gemini embeddings and some other models. These models converts the user query into a numerical vector format called embeddings. I know, you are probably thinking, wait, what exactly are the embeddings? Let's simplify this. Suppose we have this sentence, hello, how are you? To humans, it looks like simple text, but to AI systems, this text is mathematically represented across hundreds or thousands of dimensions. Each dimension captures some hidden meaning of the sentence with values ranging from -1 to +1. Some of the dimensions are social function. It scores based on how it sounds like a greeting, a command or a statement. In another dimension, it checks sentiment. Is it a happy, angry or polite way? Interrogative dimension. Is it asking a question? In our example, yes, this dimension has highest score. Formality dimensions checks for the casual or professional tone. Temporality dimension shows the time period, past, present or future. Now obviously, modern embedding models don't manually define only these 5 dimensions. They generate thousands of learned dimensions automatically. But conceptually, embeddings are basically a mathematical representation of meaning. Or even simpler, embeddings are numerical fingerprints of data. And similar meanings produce similar embeddings. That's the most important idea. Now, once the user query becomes an embedding vector, the system searches inside a vector database. Some popular vector databases are Pinecone, VV8, ChromaDB, pgvector. Now here is the special thing about vector databases. Basically, traditional databases search using exact words, but vector databases search using semantic similarity, meaning they don't search for exact text matching. They search for mathematical similar meaning. For example, ICU visiting time. When can family members visit ICU patients? May contain completely different words, but semantically they mean almost the same thing, and embeddings can help the database understand that similarity. Now how does the database know which vectors are similar? Using math, mostly something called cosine similarity, smaller angle between the vectors has the higher semantic similarity, so the systems retrieve the nearest vectors related to the user query. This process is called approximate nearest neighbor (ANN search), and internally, vector databases uses indexing algorithms like HNSW, hierarchical navigable small world, is a graph-based technique offering extremely high search speed with higher memory usage, whereas inverted file index is a clustering-based technique that offers lower memory consumption suitable for massive datasets. Don't stress too much about these names, just understand these algorithms make semantic search extremely fast. Now comes the interesting part. How companies actually store documents into vector databases, because you cannot directly store a 500-page PDF as one embedding. That would destroy semantic meaning. So first, companies collect domain knowledge from PDFs, policies, handbooks, FAQs. Then the text gets cleaned by removing headers, footers, page numbers, author names, and all unnecessary things are removed from the text. Next comes one of the most important steps in RAG, chunking. Large documents are split into smaller pieces called chunks. Each chunk may have 500 tokens with overlap of 50 tokens. Wait, why overlap is needed? Because context can break between chunks. Like in this example, chunk 12 ends with employee must submit the form, and in chunk 13 it starts with within 5 working days. Without overlap, both chunks lose meaning individually because the meaning is split across 2 chunks. Overlap preserves semantic continuity without hard limiting, so context isn't lost at boundaries. I know, you might be thinking about duplication of chunk results with overlaps in fixed size chunking. But there are some deduplication techniques used to remove the duplicate chunks from the results without losing context. But we are not going deep into these techniques now. Let's focus on RAG architecture. There are multiple chunking strategies. Fixed size chunking. As we have already seen this approach, I am not explaining it fully. In semantic chunking, companies split at natural boundaries like paragraph breaks, section headers, sentence endings, so that no context is missing. Recursive chunking is actually very clever. It tries splitting by paragraph, new line, sentence spaces until the chunk becomes very small. Now after chunking, every chunk is sent to the Embeddings API and each chunk becomes something like this, a hundreds of dimensional vector with ranging the each dimension value from -1 to +1. Then each vector is stored in the database along with metadata. So every chunk becomes one searchable semantic row inside the vector database. The whole process of extracting data from documents, cleaning text, chunking data, getting vectors from Embeddings API and storing them in vector DB will be completely automated and programmed. No human is manually doing all this scoping on each step. Companies don't just dump everything in one flat table. Perhaps they organize the namespaces, schemas, and collections based on the type of database they are using. At such time, system can either search across all namespaces with a broader view or restrict to relevant namespace with precise view. I know, initial setup for storing vectors is a bit complex, but this is one-time process. Okay, now it's time for the context retrieval process. During search, the vector database retrieves top K matching chunks, usually 5 to 20 chunks with ranking according to the scores. Then drop chunks below the threshold score, something like 0.7 or 0.8 for more accurate results. But still not all chunks are perfect. So system applies another step called re-ranking. This uses special cross-encoding re-ranking models. These models deeply analyze semantic relevance and reorder the chunks more accurately, rather than geometric calculations like cosine similarity. Now finally the system prepares the final prompt for the LLM. This prompt contains user query, retrieved context from the re-ranked chunks, system instructions like masking the sensitive data and not exposing the unnecessary information to the user from the attached context. Now the LLM no longer depends purely on memory. It now has real domain knowledge attached to the prompt. And finally, the LLM generates the response using retrieved context. And that entire pipeline from creating embeddings, vector search, semantic retrieval, re-ranking vectors, context injection to final response generation for accuracy and preciseness is called Retrieval-Augmented Generation. This is why modern AI assistants can answer company-specific questions even if that information was not part of the model training. And this architecture is becoming the backbone of modern enterprise AI systems.